Let's have a look at the Atmel Software Framework, or ASF. We'll be using an Atmel AVR in this example, but the principles and procedures are the same for Atmel ARM devices. From the Atmel Studio welcome screen, start a new project with the New Project wizard. Select the user application template for the UC3L0 XPLAINED and give the project a name, ASF Getting Started, and click OK. The template project opens. Let's get a quick success by switching on an LED. If we look in the Solution Explorer under ASF AVR32 Drivers, we see that the GPIO and Interrupt Controller drivers are already added, so we can use those functions immediately. Let's open up the UC3L0 Explained User Guide to find an LED we can use. This document can be downloaded from www.atmel.com/explained. We'll choose LED 0 next to the switch. In the table associated with the expansion header, we see that the output pin must be output low, i.e. cleared, to turn the LED on, and that the associated UC3 pin is PA11. Let's also look up this pin in the UC3L0 Explained board header file. This file is found in the Solution Explorer under AVR32, Boards, UC3L0 Explained, and open it by double-clicking. Searching for LED 0, we find that LED 0 is associated with the pin AVR32 pin PA11, which confirms the pin number from the table in the user guide. Now, go back to Main and look for a GPIO function that can switch the LED on. As we start typing GPIO, a number of suggestions pop up. The function GPIO clear GPIO pin drives a pin low, so we'll use that. This function takes a pin name as an argument, so we'll give it LED 0 GPIO. Add an end guard to your program in the form of an infinite while loop. Now, click Start Debugging and Break in the Debug menu. Step over Board Init, and then step into GPIO Clear GPIO Pin. Single step here, and you'll see that the LED switches on when a logic 1 is written to the ODERS. The value is actually set low with the OVRC, or Output Value Clear register, but the ODERS, or Output Driver Enable, enables the GPIO driver. Now, go back to the main function. Hungry for more action, let's make the LED toggle every half a second. A delay function from the ASF will help us do this. But initializing the delay function requires knowledge of the current CPU frequency. Well, the ASF also has a clock control driver module, which includes a function that returns the current clock frequency. So we should add this driver first. In order to add the clock control driver, start the ASF wizard. This can also be found under the project menu. Find the clock control driver module by starting to type clock in the search bar. Select the clock control service and click Add to Selection and click Next to see which files will be added to the project. Then click Finish. Every driver or service must be initialized. In most modules, the initialization function name is the module name plus _init. For the clock control module, which in ASF is called sysclock, start typing sysclock_init. Visual Assist confirms by giving us sysclock_init as a valid option. Clock configuration options are set in conf_clock.h, which was added to our project when we added the clock control module. Now, Add the delay driver through the ASF wizard. Type delay in the search bar, then click Add to Selection and Finish. Our delay must also be initialized, so we start typing delay init and find this function, which takes the CPU frequency in Hertz as an input argument. sysclock has a number of functions to get CPU and peripheral bus frequencies, and sysclock get CPU Hertz will be perfect. The function GPIO clear GPIO pin sets the pin to output and drives it low. Since our GPIO has already been set to output, we can now simply use GPIO toggle GPIO pin. Note that this requires GPIO configure pin to have been called, which is incorporated into GPIO clear GPIO pin. Finally, we call the function delay milliseconds with the value 500 from the while loop. The LED now toggles every half a second.